Okay, let's go ahead and get started. I'm Brenton. I'm going to be the one who's going to be demoing for the project that we did here. And I'm going to go ahead and share my screen and I'm going to walk you through exactly what we got going on. So we set out to create a robotic arm that would be able to grasp three different shapes of objects: a cylinder, a cube, and a sphere. So in that design, we landed on a 5 degree of freedom robotic arm with a claw actuator. And then Sam, he went ahead and he catted this out after we had done the mathematical modeling for it. He did that in Autodesk Fusion. And with Autodesk Fusion, we were able to get a script where you can just take the CAD, and if it's right, you can export it into a URDF, and then you can import that directly into your world. And so let's see, let me pull this up right here. You can see uh, in the ARMBot description that this is where our URDF came from when we created that transfer over. Sweet. So we have this, and then we are able to spawn it into our world, which we'll get into. But overall, the idea of our project was that we were going to use a camera to do computer vision to be able to identify the objects based off of either the shape, the color, or both. And then based off of that, we would uh, tell the robotic arm which object to pick up out of a selection. It would maneuver to the position that that object was in, grasp it, and then place it in a different location. We did run into some issues, but we did get a lot of the project working, and that's what we're going to be going over here. So I'm going to go ahead and share this screen real quick. These are our 4 terminals that we have open. You can see the first thing that I'm going to do is I'm going to launch my world, and then we'll go ahead and look at that real quick. So in our world, we have two cameras. We have a top-down camera, which is facing straight down, and then we have a camera that is coming in from the side angle. This is in the positive Y direction. We chose these for a lot of reasons. We aligned these specifically so that they would be able to identify an object, and we had to make sure that their X and Y axes were the same. There's a little bit of roll, pitch, and yaw to get these so that those X coordinates would be exactly the same. And then this top-down camera is actually pretty important to identifying the actual position of these cylinders. So we'll go over the code really quick. Actually, I'll just drag that over. I'll talk about it and then we'll do the full demo. So for the shape detection, that we used CV tools, and we ended up having to use 2 cameras. And the reason why we ended up having to use 2 cameras is because with one camera and the contour features that OpenCV has to be able to detect images, it does very well for 2D images, circles, squares, triangles, rectangles. But unfortunately with 3D images, especially things like a cylinder or a cube, which can view differently based off of the angle that you turn it, that you actually end up having a very unreliable 3D shape recognition from just one camera, unless you were to implement some type of machine learning, deep learning, which we did set up the pre-processing for and the actual training of the model. And then we implemented a version of our shape detection, which uses this convolution neural network. But unfortunately, we were either unable to find a training and test set that were robust enough to actually train our model. And if given enough time, we would have gone ahead and created those in 3D objects, like some of the papers that we've gone over in this class, and then we would have trained that neural network on that, which would have allowed us to go down to 1 camera. but unfortunately, we just didn't have the time. So we ended up having to use two cameras. So something that you're going to see as we're going to go through this is the way we were able to actually get our 3D object detection was by using combinational logic, because the top-down camera and the side camera will, depending on the angle of the object, identify them as different shapes, not necessarily the three-dimensional shape that it is. So by using combinational logic through trial and error, we were able to mitigate, the inability to have that robust data set to do that deep learning, to get a pretty high degree of accuracy in terms of image recognition, or 3D shape recognition. Now, we do acknowledge that there are limitations to this because these are, quote unquote, perfect shapes, that there's not a lot of noise and then not a lot of variation because they are three-dimensionally built in gazebo. And so with that, should we be adding deviations? We understand that this model would not be good enough, but that's why the deep learning model would be able to just easily plug into that. We just need the data set. So let's see. Yeah, we go through detect shape, where, like I said, we use the contour features of OpenCV to be able to detect those changes, those contours, and then assign shapes based off of geometry and math. So what I'm going to go ahead and do is I'm going to pull this over here, and I'm going to launch this. You're going to see that, and I'm going to drag and drop these over. So these are actually the top and the side down cameras. So you can see that the top-down camera is identifying the blue sphere, the green sphere, the red rectangle, and the side view camera is assigning the blue sphere, green cylinder, and red rectangle. And then if we pull this back out, that you're going to see that this is actually identifying it as a blue sphere, a red cube, and a green cylinder, and it's assigning them coordinates. And now we'll get into the coordinate definition of the system. So we'll pop back into gazebo. And so that's where I said that this top-down camera being perfectly parallel to the plane was actually incredibly important, because what we ended up having to do to assign these XY coordinates is we took the pixel height and width that's in our camera that we prescribed, that we took the focal lens, and then we essentially did some math based off of that and the height that the camera is off the ground to understand the exact width and height that our camera was able to view. And then we assigned those let's see if I can find this real quick. Yeah, pixel to world. We assign those pixel values. So you can see here this top-down camera, this 639, 479, that is actually the 0, 0 coordinate, because that's assigning that to the center of the green sphere, which we intentionally are going to spawn into this world in our world file. And so we took that height and that width, we broke that down, and then we assigned these X and Y pixel values to have a real world value in meters. And so you're going to see that here. And what this is going to do is this is actually going to be monitoring these shapes, and it's going to be looking for them to move. So here, let's go ahead and make this a little bit bigger. And then I'll just bring in the top-down camera and in this terminal. Ooh, that'll do it. One sec. I'm gonna pause. Actually, I'll just pop in the terminal real quick. Right, just pop in a different terminal. That's fine. Yeah, it's not good on that one again. Ooh, there we go. All right, that is going to be grab the command. We are going to do all right. There we go. We are rocking and rolling again. Sorry about that. So what we are going to see is, pull this back over, as these objects are going to move, that it's constantly monitoring them and watching them move, and it's actually publishing these locations constantly via JSON. And every time it moves, you're going to see that it's going to update and say, all right, these are the new locations that these things are at. So we can verify the relative accuracy of this based off of coming here. So this blue sphere, I just moved it. So I'm going to come here to pose. Click on the sphere, pose, and we're going to see that's x 0.56 and y minus 0.07518. And then, so there is a little bit of error that we're trying to mitigate and change, but you can see that it's 0.61 and minus 0.0135. So it's assigning these to a relatively high degree of accuracy based off of just a pixel input. Obviously, there's a lot of fine tuning to do, but you can see that even as we like kind of move these, you're actually trying to move it up a little bit, that it's going to be able to pick those out relatively well. Again, there's always room for improvement. So yeah, it's a little bit higher here. So the green cylinder is now at plus 0.054. So that's off by 1 centimeter. And then by 5 point, wait, 0.054 by, where's the next one? It's hidden for me, 0.63. So yeah, it's off by a little bit in the y direction, but it's still able to get that within enough accuracy that we said that we were successful enough to be able to move forward with this. So now the next thing that we're going to go ahead and do is, since we're just in Gazebo, I'm actually going to go ahead and close this out, and then let's see. I'm going to close out Gazebo, and then I'm going to respawn it. But this time I'm going to be spawning it with 3 shapes that are all the same, but different color. And so we're going to see that here. And again, you're going to see blue sphere, green sphere, red sphere, and then it's going to be picking out the locations of these. So that's pretty cool. So the next thing that we're going to do, since we're just in Gazebo, is I'm going to go ahead and spawn in our robotic arm, which you can see right here. So for the sake of this demonstration, I went ahead and made these shapes really big, just so that they'd be easy to see on the cameras versus the robotic arm. But we do have a version that was scaled down. And this is kind of where the project had some issues, is that we couldn't get the control manager to fully actuate. And so we couldn't be sending commands to the joint publisher or any of those things, which was a pretty big bummer. We spent a lot of time troubleshooting and trying to figure that out, but unfortunately it just didn't end up working out. But we were able to spawn it into our world. And then also we were able to, let's see, we were able to get it into RViz, where we were able to control the joints, but still, because the joint state publisher wasn't publishing globally, just because of the control manager for some reason not working in our environment, we weren't able to send automatic commands to this. But you can see that we were able to move the robot and move it around and all those fun things. So we were able to get it in the world, and it does work kinematically. So, all right, I'm gonna go ahead and close that out, and we're gonna go to one of the last things that we have. I'm gonna open up another terminal real quick. All right. All right, so I come here. Move over to our environment that we set up, and then we are going to run our user input and move it. And so this is going to be picking up the signal that is being sent from the image and shape detection via the JSON. It's going to be sending the world coordinates of these, and then it's going to prompt the user what object that they would like to pick up. And it's going to ask the color and the shape. So in case of this, I'll say, I want to pick up a red cube. Now it's going to take the coordinates that are here and say, like, hey, there's a red sphere, there's a green sphere, and a blue sphere, but the object that you want doesn't exist. Do you want to do it again? So we'll do yes. And then let's say we want to pick up the red sphere. Oh, red sphere. So it's going to look for the object and then it's going to send it to move it. And that's going to be the last portion of the project that we're going to talk about. And that was what we would have done should we had gotten the control manager to work. So we ended up using a plugin called Move It, which you can take your URDF of your robot arm and then you can send it through a setup and it will help you configure all of the different kinematics, control limits, controllers for your URDF. And then it'll automatically create those and help give you some launch files. And what's really cool is because they have these plugins that do these kinematics for you. You can see, I think it's one of these. Anyway, it will actually do the kinematics for you if you plug in a location, XYZ, and then it will send the control signals to the different joints and linkages to actually move the robot to that location. So we can see here in the select object pick that we would have implemented this move it function, and then it would have fed that X, Y, and Z position into the robotic arm. It would have taken the robotic arm there. We would have given it a grasping command, which would have moved the linkages of the claws to grasp, and then it would have picked up, moved to a specified position, and then returned back to a resting position. And one thing that's cool about Move It is that you can assign poses and then just maneuver to that specific pose. So that's what we would have done should we have gotten it moving. We have all the infrastructure into place. So even though we weren't able to get that working, as soon as we get that control manager troubleshot and figured out that we can actually go ahead and implement this very quickly and have a fully successful project. But overall, our project was fairly successful in terms of identifying the colors, identifying the objects based off location, determining the X, Y, and Z position, and then doing the mathematical and design modeling for the robotic arm. And then from there, we were able to implement it into the worlds that we had created. And then we were able to do everything but actually send an automatic signal for the robotic arm to go grasp the object and move it. I would say biggest lessons learned is that we had a really big learning curve coming into ROS. If you're not familiar with Linux, which most of the members of our team were not, that ended up being a really big learning curve. And then a lot of these different files are very unfamiliar to all of us, even those who were familiar with Linux, and just learning how to read, how to navigate, and do all of those things took just a significant amount of time. So when we did run into issues, to be able to troubleshoot them, it took a lot of time to gain the knowledge to even begin the troubleshooting. So I would say if we were to start the project now with the given knowledge that we would have ultimately, if we had been able to start over the project with the knowledge that we had now, we would have been successful in getting the robotic arm to move. There are a couple of things that we just didn't have time to try. I think the next step was to boot into a virtual machine and see if we could get an environment working in there. That didn't work to configure all of these things to work into ROS1. I mean, the Python scripts will be the Python scripts, but the URDFs and the move it and the world files, all those would just require a little bit of maneuvering to be able to get to work into ROS1. But yeah, that is our demo. Please reach out if you have any questions. And again, I'm Brenton Mizell. Thank you so much for the fun quarter.